Hello everyone and welcome to Chaos's international conference. This event has been a kind of year in the planning, so I'm so super excited to finally bring it to you and to introduce our first speaker, Professor Jasper van Wezel. He has had quite an international career already since doing his PhD in the University of Leiden in the Netherlands, and has actually been a lecturer at Bristol. So, you know, it's lovely to welcome him back and having him inspire more Bristol students. Chaos would usually make a donation or contribution towards speaker travel costs, but since no cost has been incurred by setting up a Zoom meeting, we're donating any money we would have used to the Wesmos Foundation, which advocates unlimited health for all. But without further ado, please, Jasper, talk to us about your research into ordering charge in real materials.
Great. Thank you very much, Eden. Thank you very much for organizing this conference. I think it's a fantastic idea to actually use the pandemic to do some things that you wouldn't otherwise. So yeah, I wanted to tell you about some work that I've been doing about electrons in materials. But of course, I wasn't quite sure what the audience was going to be. So I'm imagining that there's people from all years in physics, first, second, third, master level maybe. So actually what I thought I'd do is I'd begin with quite a broad introduction and tell you a bit about condensed matter physics in general and what the whole idea is. And then we'll go on to my work with electrons in materials, and I'll show you what's exciting about them. So let's first, you can all see these slides, right? This works. Perfect. All right. I even have a laser pointer. So, so first, let's, as an introduction, let's talk for a bit about emergence. So I guess if you've heard anything about condensed matter physics, you already know what emergence is. So, you know, if so, then bear with me. We'll get to more advanced parts later on. But I still think it's good to think about this every once in a while. So the idea of emergence is actually quite old. It really started maybe with a presentation that Richard Feynman gave in 1959, where he said, there's plenty of room at the bottom. And the bottom here means the small scales. So what he was really talking about is the fact that if you miniaturize things or look at things at the atomic scale, then there's a lot of freedom to make all sorts of stuff. And not just the atoms that we already know, like the periodic table, but in fact, the thing about the microscopic stills is that there's so much room. You know, electrons sit far apart, atoms sit far apart, and there's lots of atoms. And then there's many different ways in which you can put them together. So if there's 100-something elements in the periodic table, there's not just 100-something materials that you can make. You can also combine these elements. You can, even if you have only one element, you can put them in different orders and get completely different materials. And this sort of, the idea is that there's like unlimited things that you can do. You just imagine how you want the atoms. They all have different properties and different materials. So then you can wonder, you know, how do we describe all of these materials? So all of these things that we can do with atoms, and what can you get? And then actually there's another very famous article written by Bob Laughlin and David Pines in 2000, where they describe the way to calculate all of these things. And the article is called The Theory of Everything. And in it, they also present the theory of everything, as it was known at the time. It hasn't changed. So the theory of everything is one that most of you will already recognize. It's this one. So that is Schrödinger's equation, right? Written in direct notation. The only thing you have to know is that it is a Schrödinger equation with a Hamiltonian. So it's important that you specify what the Hamiltonian is. And really, this is all that goes into it. So what this says is just that, look, here's kinetic energy for atoms. So you have atoms and they can move. Then you have electrons and they can also move. And then the electrons have a Coulomb interaction with the atoms. And the electrons, or sorry, the atoms have a Coulomb interaction with each other. And also the electrons have an interaction with each other. And that's it. And this really is the Hamiltonian of the universe. Of course, you have to sum over all of the atoms and all of the electrons in the universe. It's a bit of a big sum. But if you do that properly, then really this simple equation describes everything you must know. So really, that's it, right? So we, as physicists, all we need to do is learn this equation by heart, and then sort of put in the atoms and electrons that you might have in the thing that you want to study, and go and calculate all of their properties. Of course, in practice, it's not quite that simple. And the problem, is actually a very practical, technical problem. The point is, if you have a bunch of atoms and you want to put them in your Hamiltonian and calculate their properties, you have to first, put their masses and their positions in. But then you have to consider all of these Coulomb interactions in the Hamiltonian. Actually, all of these atoms, of course, have interactions with each other. The strongest interactions are with the atoms that are nearest, closest neighbors. And, if you do it pairwise, then probably you can handle that. You can figure out what the forces of one electron are on the other, or you can put them in the Hamiltonian and describe all of their interactions. But actually, these are not the only interactions. There are also some interactions between atoms that are further apart, and even some further apart. Actually, even the furthest. Every electron interacts with every other one, and every atom also interacts with all of the electrons, and all the atoms also interact with each other. And it just really becomes one big mess. And so even with just a few atoms like here, you can see already that there are exponentially many interactions. And even if you know in principle how to describe them, in practice, you can never do it. So even for a few particles, well, it's written many particles, but many is already just a few. A few more than 20 and your computer cannot handle it. Even the most modern laptop, or even actually the superconductors that you have at Bristol, more than about 23 atoms, they cannot actually solve this Hamiltonian anymore. So the lesson is, if you have many particles and interactions, you get very unpredictable results. There's no way that, even if you know the theory of everything, that you can do anything with the theory of everything. And in fact, it's worse. This was actually just, many particles with many interactions. But let's take even the very simplest situation. Let's say that we only have atoms. And all of the atoms are exactly the same. And they all sit nicely in a row. So it's just about the simplest thing that you can imagine. Then I can write down the Hamiltonian for it. I won't do it here because it's a bit boring to write big equations all the time. But basically, it's the same Schrodinger equation, right? But now the Hamiltonian for this atoms in a row. But if I give you the Hamiltonian, do you think that you could tell me what the speed of sound is through this row of atoms? Or which color it might have if you look at it? Or even worse, what the resistivity is if I try to put a battery across it and then get some current to go? All of these things really are, they are in there in the Hamiltonian somehow, because it is the theory of everything. But how to get them out is a big question. And so this theory of everything that we have, right, quantum mechanics, it is a theory of everything that you hold in principle, and you can do a lot with it. Like I'm not trying to bash quantum mechanics or something, right? It's a very good theory. Schrodinger was a sort of a hero, and we can do lots of things with this theory. We can find out what all of the sizes of the atoms are, what the properties are. We do a lot of chemistry already. Right, so you can do chemical bonds and figure out how long and strong these bonds are. You can find out some elastic properties of matter. If you push it, how will it deform? You can see for some molecules that are not too complicated, how they can form. Often you can find the rates of chemical reactions. That's really important if you want to do chemistry. You can look at the structure of crystals and how they transition from one into the other. You can describe things like magnetism, at least ferromagnetism. So there's, this is not all, of course, there's much longer list. There is a lot of things that you can do with quantum mechanics. But the same theory of everything, even though in principle it is about everything, you cannot calculate most phase diagrams. It's too hard to just put in all of these atoms and interactions and find out what possible phases your matter has. You cannot describe things like superconductivity, where all electrons come together and conduct electricity without resistance. Also anti-ferromagnetism and other types of ferromagnetism or magnetism are too hard. And if you go on, if you give me a protein and ask me what it does in my body, it's impossible to calculate starting from quantum mechanics, let alone things like the stock market or the human brain. So even though we have a theory of everything, it's clearly not very good for calculating anything. And it gets worse. There's even some exact results in physics, like in quantum Hall effects and the Josephson effect. These are two physical effects which are where the theory, or actually both theory and experiment agree that they give very precise predictions. Quantum Hall effect is an effect in which the resistivity gets quantized, which means that it comes in very specific packets of exactly h bar over e squared, and not 0.9 h bar over e squared or 1.1, but exactly h bar over e squared. And this is so exact that you would say, okay, that is a clear mathematical result, right? That there must be a simple explanation for it. But there's no way that you can find it starting from the Hamiltonian of a piece of quantum Hall material. So clearly, you know, reductionism is kind of letting us down here. Breaking things into their smallest pieces and the interactions between them, in principle, is the correct thing to do. We can write down the Hamiltonian for it, but then we can't do anything with it. We can't calculate anything. So there's something more at work here. And the person who said it most nicely is perhaps Phil Anderson. So he said in 1972, he wrote a very famous short article, More is Different, where he argues precisely that more things are not just the sum of their parts, they're more than that, not just more, but also completely different. So the quote is a bit long, but really what he's saying is, if you put many particles together, then they start to have properties that are just not in the particles themselves, completely new properties. Like if I give you an atom and ask you what is the speed of sound going through this atom, there's no way to answer that question. A single atom doesn't have a speed of sound. But then if I put many of them together in a balloon, I can measure that there is a speed of sound going through it. Same for color, or most color. And many other properties. Many of these properties just arise when you put many things together. They don't really exist on their own. And that is the idea of emergence. So really in physics, but also in science in general, there's been a sort of a very slow revolution where we used to think that all of science was reductionism. You just break things down and see what they're made of, then you can understand all of the laws of physics, and you can, you know, put the building blocks together into whatever you want and understand everything in the world. But that reductionist view doesn't work anymore. Ever since 1972, very slowly we've been convinced that actually, besides reductionism, it's still useful to know what things are made of. But once you know that, you must also do something else, and that is understand emergence. So understand how things start to exist that didn't exist before. And one place in which this, this really comes to fruition, where this is the main thing, is in condensed matter physics. So just to give you some examples of emergence in condensed matter physics, I'll show you a couple of pieces of matter where all of their properties are determined by the electrons in them. Right? And the electrons are always the same. It's just a tiny particle with almost without mass, with exactly E of charge, and that's it. You know? But if you put these electrons together in a bit of, well, it's basically rusty copper, then this rusty piece of copper, if you cool it down, becomes superconducting. Conducts electricity without any resistance. And if you put it in a magnetic field, it starts to levitate. So somehow putting enough electrons together in the right way makes them into a superconductor. Taking the same electrons and putting them together in a different way, this is a very thin piece of metal, in a strong magnetic field, they become something different. They become a quantum Hall system. And the quantum Hall system, okay, you can't see this plot, obviously. It's just a schematic. If you've seen it before, you'll recognize it, and otherwise, just think of it as funny lines. But what this plot is really showing is that the electrons in this material become quantized. Their resistance is quantized. So whereas if you have a normal piece of wire, right, if you, for example, heat it up, its resistance changes, but it changes continuously. It goes from 1 to 1.1, 1.2, and so on. Here in the quantum Hall thing, it goes in steps. You can only have a resistance of h bar over e squared, or 2 h bar over e squared, or 3 or 4, but nothing in between. And actually, if you go to even higher magnetic fields, the same material with the same electrons becomes even stranger. All of a sudden, these electrons change completely their properties. And instead of having the charge of an electron, they become particles that have only 1/3 of the charge of an electron. So it's as if the electron breaks into 3 pieces. And it's actually not just the charge that breaks, it's also even the statistics. So you might know that if you have 2 electrons and you turn them around in the wave function, you get a minus sign. It makes them fermions rather than bosons. Well, in these materials, if you turn them around, you get 1/3 of a minus sign. So, e to the power I pi over 3. That's crazy, right? So it's not a fermion, it's not a boson, it's not any particle that should exist in the universe. It's an anyon. But these anyons really do exist inside of these materials. You know, they emerge, even though they don't exist as fundamental particles. And it gets crazier. You know, you take the same electrons and you put them in a piece of carbon nanowire. So this is really graphene, or just, you know, atoms of carbon, but then rolled up, like a little roll of material. Inside this carbon nanowire, the electron splits into 2, but not into, you know, 2 halves of what it was. Actually, an electron, as you probably know, has charge, electric charge, but also spin. It has a magnetic moment. In these carbon nanotubes, the electron splits into one particle that has the charge of the electron and another particle that has the spin of the electron. But the spin particle doesn't have any charge and the charge particle doesn't have any spin. So again, it's completely crazy, right? In the vacuum, in our normal universe, those things cannot exist by themselves. They always come together. The electron has a spin and a charge. But inside a material where things can emerge, they can take completely different roles and separate. The last one surely you've heard of, that's graphene itself, where actually the electrons in graphene stop behaving like the normal electrons that you know, and actually become super relativistic particles. You know, like all actually massless relativistic particles. So they lose all of their mass and start moving at the speed of light. Except that the speed of light inside this material is very different from the speed of light outside. In fact, it's extremely slow. You could walk past it. And tunable even. So you can change the speed of light in this material, investigate what happens when it becomes really low. So this just goes to show that, you know, once you allow for emergence, you can take fundamental particles, the things that you've broken your theory down into, put them together in different ways, and get completely different types of behavior. And that really is what condensed matter physics is about, right? Understanding this emergence of properties when we put things together inside a material. And so the message is that actually within condensed matter, so within materials, where you have this playground with plenty of room at the bottom, as Feynman said, you can make your own vacuum if you want. So for example, in this graphene, right, you can think, okay, graphene obviously is not the vacuum. There are many atoms in it. But for electrons inside the material, in graphene, they don't know that the atoms are there. They just, you know, that is their universe. They look around and they think, you know, in the universe, there's like bits of carbon every time. That's all they know. And so for them, in that universe, they are the fundamental particles in their universe. And their universe, their vacuum, is completely different from the vacuum that we are used to. So by allowing this, right, you get new types of particles. You get, for example, particles with the charge of an electron but no spin, or with the spin of an electron but no charge, or these 1/3 of electrons, or anyons. You get new physical properties, new physical laws. Like Coulomb interaction no longer has to go like 1/r. It could go like 1/r squared, or even like log r, you know, things like that. And you know, the point really is, if you can make a vacuum, you can decide what kind of particles you put in there, and you can make up your own laws of physics. Then really, you know, you're kind of playing for God, aren't you? You're just creating your own universe. And that, in the end, is what condensed matter physicists do. They are creators of new universes. Make up the laws and the particles that they want to find there. So that's emergence. Like, that's the general picture. Okay, but of course, we don't, us condensed matter physicists, don't get up in the morning and think, okay, what universe am I going to create today? What particles shall I put in it? We start by studying the universes that nature already gives us, because actually they're usually very strange. And so, okay, I don't have time in one lecture to really tell you about all of the things that we could do, but I can discuss one particular example. Right? So this is something that I've been working on over the years, also on other things, but this is one of the things. And this is about charge order. So this is one particular type of order, universe, that might emerge inside materials, and actually does emerge in many materials in nature. It's just one particular one, but it's one that I happen to know about, and that I can tell you how strange and interesting it can be. So this is basically what it is. So here we're looking at a picture of a particular material. It happens to be called niobium diselenide, but that doesn't really matter. This picture is taken with a scanning tunneling microscope. So what that is basically it's a little bit like a needle that you just push onto the surface of the material, and then you drag it around. And every time it drags over an atom, it sort of deflects and jumps over the atom, and that deflection we can measure. So you're sort of feeling where the atoms are in your material. And so in this picture, that is what you see. So these blobs, I don't know, can you actually see that? Probably, right? So this is made up out of just little circles. So each of those circles is one individual atom. And all of these atoms are exactly the same. They are all selenium atoms, and they're all in exactly the same position in this material. So they should all be precisely equivalent. But of course, they don't actually look equivalent, right? Some are bright and white, and others are dark, bluish, even black. And so you might wonder why they're not the same. Normally I would play a guessing game if I had you all in the same room, but since it's online and a bit tricky to turn on and off the audio all the time, let me just give you the answer. Okay, I'll give you 1 minute to think about it. Do you have an idea of what you might be looking at? I'm cheating a bit because I haven't really told you what the scanning tunneling microscope measures, right? What it really measures is not where the atom sits, but really how many electrons there are. So color here is really electron density. The brighter it is, the more electrons there should be. But all of these atoms are exactly the same. So it's still strange that one is brighter than the other. So what happened in this material is precisely an emergent phenomenon. Is that when you cool it down, all of these atoms, even though they are exactly the same, they start behaving differently. And spontaneously, electrons prefer to sit on some atoms and not on other atoms. And what they do actually, here on the top, you can see it quite nicely, is they make a wave of electron density. So here there's a lot of electron density, then not so much, a lot, not so much, a lot, not so much. So this is literally like a sine wave going through the material. Huh? Yes.
Just wondering, are there sort of smaller, brighter clumps? Are they sort of anomalous, or is that something even more exciting going on? Sorry. Yeah, that sort of thing.
Yeah, those are, that's dirt.
Sure, fair enough.
Yes. So, you know, it's pretty hard for nature to make a perfect crystal. So there are always some defects or atoms that are not supposed to be there. That's exactly those things. But actually, they are also more interesting to study. Once you've understood the background and you understand this charge density wave, then it becomes really interesting to find out what happens at these defects. They all have very special properties as well. And actually, this material is very special because it doesn't have just one charge density wave, like the one that's coming in here, but actually it has 3 charge density waves that interfere. So there's one coming in this direction, one going in this direction, and one in this direction. And all 3 of them interfere and make this sort of hexagonal pattern in the middle here. Okay, so that's what it is. But now let me explain to you where it actually comes from. And actually, it's really nice because charge density waves or charge order were first introduced by Sir Rudolf Peierls. I think he was in Oxford at the time, but I'm not entirely sure. Anyway, what he did is he had made a very simple observation. And he said, consider a material in which you have atoms, and all of the atoms are exactly the same. And it's a one-dimensional material, so they just all sit in a line at the same distance from each other. Like I've drawn here, right? These red balls or orange balls are atoms. And then on each atom, you put an electron, and these electrons are allowed to move, right? They have kinetic energy. Then you can calculate what the energy of each of these atoms is, or sorry, electrons. And actually these electrons will then form waves throughout the material. Because they can move, actually quantum particles like electrons can delocalize and form waves. They're not just particles, but waves also. And for every wave number, you can calculate the energy. And then typically, if you put one electron on every atom, all of these wave lengths or wave numbers will have an electron in it. And these wave numbers will not, because they're too high in energy. And then Peierls said, okay, this is very nice. This is a good model for what a one-dimensional material looks like. But he then noticed something very interesting. And that is, you can now do a thought experiment and move some of these atoms. And if you move them closer together, like so, then of course, moving atoms around costs energy. Right? There's like forces between the atoms, which act like springs. So if you move atoms together, you're compressing a spring. And that, according to Hooke, costs you Hooke's law of energy. So the energy cost is proportional to the displacement squared. But Peierls noticed that if you now take this configuration and again calculate what all of these energies of the electrons are, you get something that very much looks like what you had before, except that over here, the figure has changed. So these energies have become a bit lower and these have become a bit higher. But again, if you put one electron per atom, then actually they sit in all of these energies and those don't have electrons in them. So actually the energy of all the electrons that were there was pushed down. So even though it costs energy to move atoms, because you're compressing springs, the electrons make a wave going over all of these atoms, they actually gain a bit of energy. And then Peierls calculated how much that gain is, and this here is the delta is proportional to U. So if you now make a very small displacement, if U is small, then U squared is always smaller than U, right? For U smaller than 1. So actually, if you do this, you can gain more energy with your electrons than you have to pay by moving your atoms around. And if you can gain energy, well, then nature does it itself. So actually, what Peierls argued is that if you start from a material with atoms that are just evenly spaced on a line, that thing will never exist. It will spontaneously dimerize and move atoms around. And as it does so, then actually also the electron density changes. And now, because these things are together in pairs, actually, there's more electrons here than there will be here. So if you look at the electron density, there will be high density, low density, high density, low density, high density, low density. And it will look exactly like the kind of wave that I showed on the previous slide. So this is the idea. This is how charge order arises. Okay, if you want to be practical, you can say in the real world, things are not one-dimensional. You should really worry about three-dimensional materials. And then there are some details to think about. So for the experts, you need to think about nesting and interactions and how they play a role. But really, those are details. For the purposes of this talk, and for most purposes, you can just forget about them. So the idea is really this, that if you move atoms around, it costs energy. But if at the same time your electrons gain energy, that might not be a problem. That still happens spontaneously. There is another way of looking at exactly the same phenomenon. And that way was, found out a couple of years later, I think in the 1980s, if I remember correctly, by Walter Kohn. He died recently. He was also a Nobel Prize winner. Very smart man. And he thought about exactly the same problem. But he said, okay, that's all very nice, Mr. Peierls, but what you were talking about is the ground state of this material, right? The state that nature would prefer the most, the minimum energy state. But actually, if I put this material at really high temperatures, then it's not in its minimum energy state. It will be in some thermal distribution. And actually, at high temperatures, these atoms can all sit at the same distance from each other. In fact, that is what they will prefer to do. Things become more and more symmetric if you heat them up. So at really high temperatures, it will be like this. And then when I cool it down, then, okay, you're right, Mr. Peierls, things will move and spontaneously dimerize. But then Walter Kohn said, maybe the nicest way to sort of describe this is not to think of the electrons, but rather of the phonons. So phonons are actually emergent particles that don't exist outside of materials. But what these particles describe is the movements of atoms, or actually the vibrations of atoms. So if you want to move atoms around, another way of saying that is that you introduce phonons into the material. And so what Walter Kohn argued is that if you take your material and you start at high temperatures and then you cool it down, at some temperature, spontaneously the atoms will start to move around. But if they spontaneously move, then that means that it does not cost any energy to create phonons in the material. Because phonons are like displacements, and apparently these displacements happen spontaneously. So if you think about these phonons as particles of displacement, then you can look at their energies. Don't worry too much about this diagram, but you can think of the energies of displacement. And at really high temperature, it costs energy to displace phonons. But then if you lower the temperature, it becomes two temperatures on this scale. So this is the high temperature curve, and then it's lower, lower. And the red curve is exactly at the transition temperature. And exactly at that point, it doesn't cost any energy anymore, zero energy, to make displacements, and the displacements will happen spontaneously. For those of you who've done field theory already, so the nice quantum field theoretical way to write this process is with diagrams like this. So just very quickly, a wavy line is a phonon. These things with arrows on them are electrons and, well, anti-electrons in a material. So those we call holes. And what you can see is that the phonon changes by interacting with the electron. It gets you a new renormalized phonon. That's the one that goes down here. That's just if you know diagrams already. What is nice about Walter Kohn's way of looking at this charge order is that it sort of tells you that this softening of the phonon, the fact that you have to pay less energy to create displacements, you can see it must come from the interaction of phonons and electrons. So in this, the nice thing about this field theoretical language is that you can just look at the picture, right? And I don't have to write any equations. So you see what happens here is that a phonon, oh, here you can, this is actually just a blow up of this part. So you can see that what happens here is that a phonon comes in, comes flying by, a wave of displacement, and then it hits an electron and scatters it into another electron. So the electron changes its momentum by scattering from a phonon. And this happens with some probability. That's what the dot means. And this probability here is, it depends on k, the momentum of the electron, q, the momentum of the phonon, and also on alpha and beta, which are the orbital quantum numbers of the electron. So it actually depends on a lot of things. It's quite a complicated object. But the nice thing about this description is that you see it must be important, right? Because it actually tells you how and when this phonon will get zero energy. Okay, so so this is really a charge order. This is how it works in the model, and how you should think about it. But now let's look very quickly at 3 specific materials. I'll go very quickly through the rest because it's really just highlights of what you might find in nature. But there are 3 very nice examples of what can happen. They're all sort of special emergent states, types of charge order that you can find in nature. There are 3 materials that I happen to have worked on, and I'll describe some of the things that we found. Mostly I'll show pictures. Yeah, and then afterwards we can maybe discuss. Okay, so the first is niobium disulfide. Never mind about the atoms that are in it. The chemical formula is here. It doesn't really matter. What it looks like is this. So there's like sheets of niobium sandwiched between sheets of selenium, and then those sandwiches. Well, there's many of those sandwiches. Here's one, here's another, and then of course there's whole stacks of them. But in between there's a whole bunch of nothing, a big gap. So this is really a layered material. And that's actually important for all of its properties. I'm not going to explain too much why, but that is what it looks like. So then experimentally, what we know about this material is that there is charge order in it. So actually you can measure that quite nicely using X-ray diffraction. And here you see if you cool it down enough, below 30 Kelvin, so that's 30 Kelvin is cold, but not extremely cold. Well, I mean, you wouldn't want to sit at 30 Kelvin, but It's not very hard for a physicist to reach 30 Kelvin. So if you get there, it charge orders. So then these atoms start to move around and you get waves of charge density. CDW means charge density waves. If you cool it down even further, there's also superconductivity. But for us, that's not so important. We only worry about the charge order for now. Actually, the superconductivity in this material is kind of famous, but that's a whole different story. So if you look at this charge ordered phase, then actually it turns out to be very strange. So this here is is data from another experiment, an experiment called RPAS. And what this shows you, so what this figure shows you is actually momentum space. And these lines here are where electrons with zero energy sit in momentum. And normally what you would find here is like closed shapes, circles or squares or even weirder figures, but always closed shapes. What is strange about this material is that you can find here a line which then ends. So it doesn't close onto itself. If you know about Fermi surfaces, this is a Fermi surface, and it seems to be a Fermi surface with a gap in it. Now that is, again, one of these impossible things that you would think can just never happen. Because what it really means is that there are electrons here going around. You could really literally think of them as just flying here and then disappearing into nothing. And that's weird, you know. Electrons aren't supposed to just disappear and not be there anymore. We have actually seen this before in other materials, actually, especially in high temperature superconductors, which are really weird materials that superconduct at very high temperatures, 200 Kelvin, almost room temperature. But these materials are famous for being impossible to describe. We don't understand high temperature superconductors at all, not even the first thing about them. And one of the special things that we don't understand in them is these arcs. But here we see the same thing, the same arcs coming up in the charge ordered phase of a material that is not a high temperature superconductor. So perhaps we could learn something about it. And actually it turns out in this material, so I don't know anything about, I'm not going to say anything about high temperature superconductors. I'm just going to say something about this material, but in this one material, we do understand where these things come from. And the nice thing is, you can actually understand it quite nicely, exactly in terms of what Walter Kohn taught us. So if you think about the scattering between electrons and phonons, then he said, right, the probability for the scattering to happen is determined by this weird function that depends on so many different things. Now, it turns out that the momentum dependence of this function in this material, niobium diselenite, is very strong. And it so happens that the electrons here scatter much more than the electrons here. And so what happens is that you, well, that's the hand-waving version of it. So what happens is that because of that, you really see the electrons only in certain places and not in others. And so we can actually model this. So you can write down the Hamiltonian for niobium diselenite, simplify it as far as you can, and put in the shape of this electron-phonon coupling, and then calculate what you would see in an experiment if you tried to do this experiment on it. So that's what we did. And here you go, that's the result. So just to compare, this point here that's labeled gamma is the middle of this figure. And so this lower circle is this circle here. As you can see, there's no gaps in it. And this thing here is, it's tilted a bit, but that's this thing here. You see this arc here is precisely this arc here, and then those two gaps are those two gaps. So you see, if you just take this momentum dependence into account and calculate the charge order in the presence of this electron-phonon coupling, then you get precisely this result, and it explains why you see some electrons and not others. Now, once you know that, you can also go on. So actually, this material that I showed you before is the same material, right? One with the wave and then the hexagons. Actually, this material is very weird. So this was another study where we took large pieces of this material and looked at it. And sometimes you see these weird things, like you have perfectly nice charge order here, and all of a sudden it becomes striped and very bright. But also here, even in 3 different directions. Turns out those pieces of the material are a bit more stretched than other pieces. And again, you know, if you have these calculations with the electron phonon coupling, then you can actually predict, like, if I start stretching or straining my material, then when will it change? So 3Q here means this hexagonal phase, and 1Q means this stripe-like thing. So you have to push it above like 0.1% strain, and then you see that it does something. Or if you strain it the other way, it goes a little bit further. And actually, we can then compare this to experiments. This is another experiment. Actually, they don't measure the charge order here. They measure the superconducting transition temperature, but they are related, because if there's more charge order, then there's less superconductivity. So if you take this thing and put it on its head, then superconducting transition temperature is kind of like the charge density temperature. And you see this shape precisely reproduces this shape. So we can actually understand the charge order in this particular material, monovalent I, quite well. And what's important about it is that the momentum in this electron phonon coupling determines everything about it. Okay, second example. That's a bit more exotic. So now we'll talk about titanium diselenide, which again is a material with a structure very much like this. So it's layered sandwiches. It also has charge order, much higher temperatures, 200 Kelvin, really not that cold, minus 100 or so in Celsius. And it has charge order, and with this charge order, all of the atoms move, just like Peierls and Cohn told us, right? If you get a charge order, then the atoms have to move. So in this particular material, they move in the direction of these arrows. This looks like a drawing, but this is actually results of an experiment. So we can actually measure the displacements of all of these atoms. But you might ask, like, why do they move in this direction? Because actually the direction is kind of strange. It is not, as Peierls said, you just move the electrons close to move the atoms closer to the electrons, and then you have the charge density wave and the displacement wave on top of each other. These actually turn out to be transverse displacement waves, which is a bit weird. But it's possible to get those, actually, if you take the second ingredient of this electron phonon coupling. There was also these orbital labels. So I can tell you quite nicely in pictures what these orbital labels mean. So let's try to describe a charge density wave now in a two-dimensional materials. So going one step further than Peierls. Then you have atoms sitting not on a line, but rather in like a square grid. And for some reason, let's say, I will try to make a charge density wave on it. So that there's high charge density here. So lots of electrons here, very few electrons here, then lots over here, few over here, and lots over here, and so on. Then what Peierls said is very simple, electrons have negative charge. These atoms are positively charged, at least the cores are. So if there's lots of electrons here, then the cores will want to move towards where the electrons are. So in this material, they will move like that. That's precisely what Peierls would predict. Okay, but the atoms that we used here were circles or spheres, really simple atoms, atoms. You also have electrons or electron states in materials that are not spherical. So in some materials, it might be that all of the electrons actually sit on like these elongated orbitals. These are px orbitals, if you want to know. So now if you try to do the same thing, you have an arrangement of squares of these orbitals, and you try to say again, okay, there will be lots of electrons here, none over here, lots here, not so many here, lots over here, and so on. And again, the atoms will want to move towards the electrons. But now, because these things have a shape, it's actually much easier for them to move in this direction than it is to move in that direction. But not all directions are equal anymore, because this is not a circle. And so, if you start displacing this material, they'll move like this. So not directly towards this this line, but rather at an angle to it. So going from a purely longitudinal wave, like we had with these circular atoms, if your atoms have a shape, you can actually get a transversal wave of displacement. And this now happens to be precisely what happens in titanium diselenide. So here I've drawn titanium diselenide, or some of its atoms. The big balls are titanium, the small ones are selenium. Actually, red is on top and green is on the bottom. You can sort of see that 3D picture. And in this layer, there is charge order, but works in such a way that it only involves some of the orbitals. And the orbitals that are involved look like this. So there will be a lot of electrons sort of in between here and in between here. And then because these orbitals have a shape, they move sort of easily along these double lines and not so easily along other lines. And that gives you the particular arrangement of displacements in titanium diselenide. And actually, along with that, then comes a prediction. Some of these orbitals in the material, some shapes of the electrons, will be more occupied than others. But actually, if you look at this material and you look at the electrons on every atom, they look like they have a shape. And these shapes are the ones that are drawn here. So this was the prediction from theory. And actually, because these all have a shape, they get very different properties. So for example, if you send a current through them, the current will feel that there's like shapes of electrons that are moving through, and they will start to rotate a bit. And actually, you can measure that. So there was an experiment not so long ago where they actually put some titanium diselenide in between two electrodes and then showed some laser light on it with like circular polarization. And you could see exactly that these orbitals are, they behave a bit like a corkscrew. They have a handedness. If you can see, these are in the XY plane, these are the YZ plane, and these are the XY plane. And so if you go from one to the other, you sort of turn counterclockwise as you move through the material. So this turning you can then measure in this type of experiment. So in this material, actually, it turns out that the orbitals played a major role, and then they dominate the physics. All right, one very final example of what you might get. Actually, this is even shorter than the others. This is, again, titanium diselenide, same material that we just looked at. Because actually it is special in a second way also, not just because of its orbitals, but there's something special about this charge order itself. So actually, so again, this is what it looks like. It's a layered material. It has charge order at 200 Kelvin. But also, if you look at the energies as a function of momentum, okay, far off here, then actually it turns out that there are some the electronic states here look a bit special. There's a band of electronic states here, and then another one over here. If you've never seen band structures, forget about it. It just means that there are some electrons, low energies at particular wave numbers, long wavelengths, and there's high energy states at longer wavelengths. But the important thing about it is that there's a gap in between. And that gap is actually really exciting because of, actually, again, Walter Kohn. It's the same Walter Kohn who in 1967 predicted that in addition to what Peierls and Kohn told us about how you get charge order, there's a second possible way of getting charge order. So if you don't know what this diagram means, it doesn't really matter. But these things over here, on this line, there are electrons. And on this line, there are anti-electrons. Or actually, it's the other way around. Sorry. Here there are electrons, and here there are anti-electrons. Positrons. But positrons inside the material are not called positrons, they're called holes for some reason. So they're electrons and holes. And what can happen here is that, of course, the electrons have a negative charge, and the holes have a positive charge. And if this gap is small enough, then it might happen that you excite an electron and a hole, and they come together, and they attract one another, just like the proton and the electron would do in a hydrogen atom. And then they can bond together and form like a neutral atom. So this electron can start going around this positron or hole as if it's together a single atom, like a neutral atom, not an ion. So such a thing you call an exciton. And what Kohn showed is that if you have lots of those excitons and they all come together in the same quantum state, they form a Bose-Einstein condensate. And this condensate looks exactly like the charge order that Peierls and Kohn described before in terms of phonons. So it is really not the same thing. It's not a Peierls instability. There are no phonons here, no displacements in the lattice. There's just bound pairs of electrons and holes. But the result is very much the same. It's a wave of density, a wave of electron density, where the electron density goes up, down, up, down, up, down. And actually, if you make it this way, that is super exciting, if this would really exist. Super exciting, because if you could take this state and then suppress the charge density wave, it might make a superconductor. And if you create a superconductor out of excitons, then actually it's been long known that there is no limit to its superconducting temperature. So it could then easily be a room temperature superconductor or even much higher temperatures. So people are really interested in finding one of these excitonic insulators or excitonic superconductors. The question, however, since 1967 has been, can such a phase actually exist in any real three-dimensional materials? This was a nice proposal, but it's purely theoretical. So the question is, if you have a material and you see a charge order, how would you know whether it's made out of excitons or phonons? Right? Because in the end, it's both are charge-ordered materials. So actually, Kohn already answered that question. For the normal Peierls-like material, or Peierls or Kohn-like material, right, you can look at the phonon. So this is again the phonon, the same picture that I showed you before already. Where this phonon, its energy goes down to 0, right? And then at 0 temperature, you can make these displacements in the lattice. And there might be an exciton also in the material, but it doesn't do anything. It doesn't have this dip. Whereas in the excitonic condensate, the one that Kohn proposed, you'd have the phonon and the exciton. It is actually the phonon that does nothing and the exciton that comes down to 0 energy. So if you could measure these things, then you could definitely distinguish. You could say either it's the phonon or the exciton that goes to 0 energy. So it turns out we can do that, or very recently we were able to do that in titanium diselenide. This is the data. It's really hard to look at, but what you can see here is that high temperatures, you have an exciton here. So this is really this mode, right? It's the exciton. And then once you lower the temperature, you go to these bluer things. Actually, this mode goes down. So follow this blue line, for example. See, it dips down and becomes almost 0 energy. And actually, for the orange dots, it is so much 0 that this is just the error bar. We can't see where it is. It's at 0, you know, within this error bar. So what you see here is actually, it is exactly this exciton going to 0 energy. And what it means is that pairs of electrons and holes, these bound pairs together, condense and form a charge density. So this is the excitonic insulator. And since these electrons and holes really come together into a single atom, you might as well give it a new name. It's not hydrogen because there's not a proton in the middle. There's a hole in the middle. So it's not, it's not hydrogen. It's also not helium or chromium or vanadium. It's made of an exciton. So people have called it excitonium. And so actually when we found this result, we published a paper with excitonium in the abstract because somebody called it excitonium before. And then the popular press got hold of that, and there was a whole embarrassing flurry of activity on the internet, actually, and even some artists trying to make impressions of excitonium. I don't know exactly what this is supposed to be, but this is supposed to be titanium diselenide with excitonium in it, and these are like, I don't know, lightning bolts of excitons or whatever. But actually, if you Google excitonium, you'll find this picture all over the internet. Right, but the point is, so this excitonium, excitonic insulator, can actually exist in titanium diselenide. But it is not quite what Kohn had in mind. So it is true that the exciton went down and came to 0 energy. But actually, at the same time, there was also a phonon that went to 0 energy. So what you find in this material is actually, 50% excitonic insulator and 50% just Peierls charge order. That is already a lot better than many other charge order materials like niobium diselenide. Right? Here it's really only the phonon and the exciton does nothing. So there it's like 99% phonon. But in this material, they come together and it's 50-50. So that's a lot better, but it's not the 100-0 that Kohn had in mind. And if you make a superconductor out of it, it will certainly not be a superconductor at room temperature because there's way too much phonons in it still. But still, since every real material has phonons in it, that are unavoidable, this is as close to an excitonic insulator as any real material will ever get. You can never get under 50%. So, in conclusion, right, what I've tried to show you sort of is to highlight charge order as an example of emergent physics. So already with just this one charge order, I've shown you that you can get very different things, like electrons can spontaneously organize into waves, and these waves can interfere and form weird patterns. They can have Fermi arcs and things that you wouldn't expect normally. They can also organized into specific shapes and give you orbital order. So that actually the electrons inside this material get a handedness and get very different properties because of their shapes. And even you can get completely new phases like excitonium, which is like material made out of building blocks, or even the building blocks didn't exist in the vacuum. You first make an exciton and then make excitonium out of it. But the lesson in all of this is really that this is just an example, right? The point is, if you put many things together, they become completely different from what they were before. They lose all of their microscopic properties and become something different entirely. Thank you.
Wow, thank you, Jasper. That was incredible. I have never actually come across emergence before, not in any of my uni modules. And it's just mind-boggling, really. So
in that case, look up the article by More is Different. It's like 2 pages, literally, and it's very readable.
It was featured at the beginning of the 3rd year solid state. So you have something to look forward to, Eden.
Gosh, well, I haven't chosen my modules yet, so you know.
It's compulsory.
Oh, well then.
You'll have to. Thank you so much.
Yes, and I don't know if anyone else heard, but at the start, Orlando and I were saying to Jasper how everyone seems to miss all these kind of small seminar groups. So we're wondering, we do have Mentimeter, and so you're welcome to submit your questions there for Jasper. But if you wanted to unmute and ask questions as if we were in a lecture theatre or a seminar room, that would be lovely. Yeah, I think anyone can unmute, I believe. Mm-hmm. So, but until other people have got some questions, I just wanted to ask with emergence. So, do you think there is a theory of everything that would kind of help us understand emergence, or do you think there isn't a theory of everything?
No, there's not a theory as such. So, the nice thing about reductionism was that we just look for the fundamental laws of nature, right? And then these became quantum mechanics or general relativity or things like that. And there's one law describing all of it. The thing about emergence is that different properties can arise every time that you put things together. Like the same electrons put together give you excitonium, but also the orbital order and all these other things. So actually, every time you put them together, you have to think again, what will emerge and why? But so we don't have actual laws, but we do have principles. So the way that you can try to study these materials always follows the same sort of routes. You can use techniques like perturbation theory. Well, there's many techniques, right? Denormalization group, things like that. So using these, you sort of starting from what you know, you can try to see what kind of physics might emerge. And since these techniques are always the same, you actually get quite far studying all sorts of materials. But every material that you study, you do have to start again. But that's also the beauty of it, right? You can find a completely new universe with just the next material.
And is our sort of understanding of emergence versus reductionism entirely limited by our computational ability to compute like all those interactions? Or is there something?
Yeah, but I mean, that sounds like a very practical problem, right? Like you just build a bigger computer and you're done. But the thing about quantum mechanics is it works in Hilbert space. You're 3rd year, right? So you must know.
Yes, yeah. Flashbacks.
So Hilbert space just means it is all the possible configurations of quantum particles. And like classical particles, you can give a velocity and a position, and that's it. Right? That's all you can do with it. But in quantum mechanics, you also have to take count of all the superpositions that you can make. And what this means is that the configurations actually don't live in configuration space, but in Hilbert space. And Hilbert space is extremely large. It's exponentially large. So even if you only have spins, forget about the masses and just make it as simple as possible. Then with n particles, the size of Hilbert space is 2 to the power n Basie states. So that's huge, right? And that 2 is really the absolute lower limit. It should be more like 100 to the power of n. So it's crazy, right? For 10 to the 23rd particles, like you have in any normal piece of material of about 1 gram, there is 2 to the power 10 to the 23rd possible states that it could be in. So there is no computer you can ever dream to build that will ever calculate that. That's all.
There have been some
Not
really,
effectively.
really interesting advancements in sort of applications of machine learning to sort of material science. I don't know if you've come across.
Yeah, there are plenty. Yeah.
Yeah. It sort of sidesteps that a little bit, I think.
Yeah, but it's a bit phenomenological, right? So you try to let the machine make educated guesses about what kind of order might emerge, and they get better and better at it. Just like humans, you know, if you have a physicist who's well trained in condensed matter physics and been studying it all his life, they can make a pretty educated guess of what you might find in any material. But just like physicists, machines will be limited by the things that they've used to train themselves. So actually completely new things, the surprises and the real breakthroughs, the really exciting things, they will never guess.
So what have been some of your like really exciting experiences during your research then? Any particular highlights?
During my own research? Well, there's plenty of interesting ones. I don't know. I mean, discovering all of these types of order that I've been telling you about, this orbital order and exciton order, that's quite exciting. Right? They're really new types of matter that just didn't, well, they existed, but we didn't know about them before.
So exciton, is that it's an actual matter, as you say?
Yes, in a sense, except that it only exists inside the material. You can never take it out.
Okay. Do you think in the future there would be a way of making it?
Well, so we can make it. You can make it in titanium bisulfide.
Outside the material?
No, that's the point. That's impossible, because outside the material, we know the laws of the universe, right? It's our standard model. And our standard model doesn't include any holes. So you can also not make particle-hole pairs. Holes only exist inside the material. So that's the point about the emergent phenomenon, that it sounds like you have a single particle, but actually that single particle, that hole, is really made up out of all of the other electrons in the material. And then when you look at really low energies, you don't see all of these individual electrons anymore. You just see some emergent property. And that looks like a hole. I mean, the best way to think about it is like sound. The sound that you hear right now in your ears, it consists of sound particles, if you want, sound waves. But these waves are not individual particles. They really consist of all of the air molecules in the room and in my room and all of the electrons in between us, you know, vibrating in sync. And that synchronized dance we experience is one single particle at one frequency hitting our ears. So it's the same with excitonium. This whole is really, it's like a synchronized dance of all of the electrons in the material, which looks to us like just one particle.
I hadn't thought about it like that before. I'll tell Stephen Dugdale, our lecturer on that, how I think he would explain it.
I'm sure you appreciate it. Yeah.
I realise we're a little bit over time, and people generally have stuff starting on the hour, so thank you for hanging in there. Does anyone have any sort of final questions? If not, could I just possibly finish with one of them? I'm sure we can.
Yeah, of course, go for it.
Could carry on forever, but you've obviously come and talked to us this afternoon for you. What will the rest of the day hold? What is it that you really do from day to day?
That changed a lot over the past year with COVID coming out. On a normal working day, I don't know. I do teaching. Actually, at this moment, I'm not teaching any courses, so that I'm off in that respect. I do research, where I actually do calculations, but also research involves a lot of working with students, PhD students, postdocs, but also master students and lecturer students. I have actually quite a big group of students who all work on different projects with me. Then you have to actually tell the world about the research that you do. So you write articles, you give talks like this, you go to conferences, and that actually also takes a lot of time. Then there's a university to be run. So there's some chores to do inside the university. And of course, with all of these people in the group, you have to sometimes get a bit of money to fund your research. So there's also quite a bit of time spent on just organizing everything, making sure we get enough money to keep things going. Mostly those things. And of course, the most fun things of those are teaching, working with students, and doing research.
Thank you. Of course, you have to say that to a group of students.
Because it's actually true. Well, I'm really just saying, enjoy it while you can. Being a student is the best thing.
Oh, well, thank you so much for coming. And yeah, oh, you're getting some round of applause, but thank you so much. It's been incredible, and yeah, mind-blowing for me. I hope for everyone else as well. So thank you.
Thank you very much. It's really nice having you.
Well, have a lovely rest of the day, everyone else. Check back on the schedule for future speakers. We have some equally brilliant talks coming up, and we hope to see you there.
Great. Thank you very much, everyone.
Brilliant.
Thank you all.
Thank you.
Cool. And thanks, Eden. It was really nice to organize.
No, thank you so much for coming. It was brilliant.
Yeah, it's fantastic. Cheers.
Thank you.
Bye.
Hope we can keep in touch.
Absolutely. Yeah. It'd be lovely to come to Bristol again.
You're based in Leiden, right?
Amsterdam.
Amsterdam. Okay. Cheers. Leiden's just a little way outside, right?
Yeah, it's like 1 hour.
Yeah, perfect. No, yeah, when I love to keep in touch and when I'm over there, if that's possible.
Yeah, as soon as traveling is allowed again, I'll be happy to come to Bristol and visit.
Sure, yeah, of course. That would be lovely to have you, of course. Brilliant. Well, have a great rest of the day, and thanks again.
All right, thanks.
Yeah,
See you.
thank you.
Thank you. Bye.
Bye.